One method for describing the electrons that exist in covalent bonds is to evoke hybrid atomic orbitals. But we must also learn how to describe these electrons by using molecular orbital theory. The way we do this is by drawing molecular orbital diagrams. With these, we will depict the molecular orbitals that result when covalent bonds form. When sets of atomic orbitals overlap, they will generate two molecular orbitals, one of which will be bonding, like the sigma px orbital, which will be the lower energy orbital, and the other of which will be anti-bonding, like the sigma star px orbital, which will be higher in energy. This works for pi orbitals as well, where the overlap is lateral rather than direct. Again, there will be a bonding and anti-bonding orbital, and this overlap can be either in phase or out of phase. Just like any other type of orbital, each molecular orbital can hold two electrons, and we fill them just like atomic orbitals, according to the Aufbau principle, from lowest energy and then upwards. Hund's rule also applies, so that for a set of degenerate orbitals, they will all be half-filled before any of them contains a second electron. Let's take a look at a molecular orbital diagram and discuss the names of the orbitals. From two s orbitals, we will get a sigma bonding orbital and a sigma star anti-bonding orbital. From 6p orbitals, we get a sigma bonding orbital and a sigma star anti-bonding orbital, as well as two pi bonding orbitals and two pi star anti-bonding orbitals. The number of orbitals is conserved when atomic orbitals become molecular orbitals. If we wanted to show the molecular orbital diagram for a particular molecule, like O2, the first thing we would do is simply place the valence electrons in the atomic orbitals on the side, which are filled just the way we would generate an electron configuration for an individual oxygen atom. Then we shift them over to the molecular orbitals and fill them up according to the Aufbau principle. We can see that the electrons from the two s orbitals will end up in the sigma bonding and anti-bonding orbitals. And then for the 8 electrons in the 2p orbitals, 6 of them will fill up the sigma and pi bonding orbitals, and the last 2 will go in the pi anti-bonding orbitals, 1 per orbital, because of Hund's rule. Molecular orbital theory succeeds in describing bonding behavior where other models fall apart, such as explaining the paramagnetism of something like an oxygen molecule. So it definitely describes covalent bonding in a sophisticated way. This is why it is important to discuss molecular orbital diagrams.